Hello everyone, welcome to our channel SKI Class Academy Learn to Rise. In our last video, we have seen designing a simple neural network for a simple real-time problem. In this video, we will be discussing about how a prediction is made by a neural network while undergoing a process and how a neural network learns from its mistake during the prediction. So we will continue our lecture from the last lecture slide. Let's start with a really high level overview so we know what we are working with. Actually, neural networks are multi-layer networks of neurons that we use to classify things and make predictions, etc. So the diagram shown here is a simple neural network with 5 inputs, 5 outputs and 2 hidden layers of neurons. And starting from the left, we can explain that first is the input layer of the model, which is given in orange color, and next to that is our first hidden layer of the neurons given in blue color, and our second hidden layer of the neurons given in magenta color, and finally the output layer or the prediction of our model is given in the green color. The arrows that connect the dots shows how all the neurons are interconnected and how data travels from the input layer all the way through the output layer. So later we will calculate step by step each output value, and in this video we will also watch how the neural network learns from its mistake using a process known as back propagation. What exactly is a neural network trying to do? So like any other model, it's trying to make a good prediction. We have a set of inputs, a set of target values, and we are trying to get predictions that match those target values as closely as possible. So forget for a second the more complicated looking picture of neural network presented in the previous slide, and let's we focus on the simpler one now. So this is a single feature logistic regression. We are giving the model only one x variable expressed through a neural network. So for those who really don't know about regression, so we will make a separate video exclusively for linear regressions. So those who want, please leave your comment after watching this video. To see how they connect, we can rewrite the logistic regression equation using our neural network color codes. So let's examine each element. Let's take x given in orange color is our input, the learn feature that we give to our model in order to calculate a prediction. And b1, which is given in a combination of blue and green, a turquoise color, is the estimated slope parameter of our logistic regression, and b1 tells us how much the log odds change as the input x changes. So notice that b1 lives on the turquoise line, which connects the input x to the blue neuron in the hidden layer 1, and b naught given in blue color is the bias, so which is very similar to the intercept term from regression. So the key difference is that in neural networks every neuron has its own bias term, while in the regression the model has a singular intercept term. So the blue neuron also includes a sigmoid activation function, so denoted by the curved line inside the blue circle. So remember, the sigmoid function is what we use to go from log odds to a probability. So do a control of search for sigmoid function in my previous post. And finally we get our predicted probability by applying the sigmoid function to the quantity, that is b1 star x plus b naught. The first hidden layer consists of 2 neurons. So to connect all 5 inputs to the neurons in the hidden layer 1, we need 10 connections. So this image shows just the connections between the input 1 and the hidden layer 1. So note our notation for the weights that lie in the connections. So w1 comma 1 denotes the weight that lies in the connections between input 1 and the neuron 1, and w1 comma 2 denotes the weight in the connection between input 1 and neuron 2. So now let's calculate the outputs of each neuron in the hidden layer 1, that is activation. So what we are going to do is we are using the formula where w denotes the weight and in denotes the input. So to calculate the activation z1, which is equal to weight 1 into input 1, that is weight w1 multiplied by input 1 plus w2 multiplied by input 2 plus w3 multiplied by input 3 plus w4 multiplied by input 4 plus w5 multiplied by input 5 plus the bias value of the neuron 1. So this gives the value z1, and this z1 will be used to find the activation to calculate the activation. That is, neuron 1 activation is equal to sigmoid of Z1. We can use matrix max to summarize this calculation. So remember our notation rules once again. That is, if it is W4 comma 2 means it denotes the weight that lies in the connection between input 4 and the neuron 2. So for any layer of a neural network where the prior layer is m elements deep and the current layer is n elements deep, means this generalizes to matrices of W multiplied by matrices of X plus bias matrix equal to matrix Z. So where W is n by m matrix of weights, that is connections between the prior layer and the current layer, and where X is our m by 1 matrix of either starting inputs or activations from the prior layer, and bias is our n by 1 matrix of neuron biases, and Z is our n by 1 matrix of intermediate outputs. So in the previous equation, the Python notation at is used to denote matrix multiplication. So once we have Z, so we can apply the activation function, that is sigmoid in our case, to each element of Z, and that gives us our neuron outputs activations for the current layer. Before we move on, let's visually map each of these elements back onto our neural network chart to tie it all up. So bias is embedded in the blue neurons. So by repeatedly calculating Z and applying the activation function to it for each successive layer, so we can move from input to the output. This process is known as forward propagation. So now note that we know how the outputs are calculated. So it's time to start evaluating the quality of the output and training our neural network. In a neural network, changing the weight of any one connection or the bias of the neuron has a reverberating effect across all the other neurons and their activations in the subsequent layers. So that's because each neuron in a neural network is like its own little model. For example, if we wanted a 5-feature logistic regression, so we could express it through a neural network like the one on the left, using a singular neuron. So each hidden layer of the neural network is basically a stack of model. Each individual neuron in the layer acts like its own model, and whose outputs feed into even more models further downstream. That is, each successive hidden layer of the neural network holds yet more neurons. In this video, we have learnt about how prediction made by a neural network due to a process of learning. In our next video, we will discuss in detail about the various schemes of neural propagation and cost function. Please subscribe our channel and click bell icon for getting updates about the industry ready skills updation. Thank you for watching the video.